What's up, General Science? It is Miss Marshall coming at you with week 3 of beautiful notes involving chemistry. Hi, what's up? How are you? How you doing? I miss you all so much. So we're going to be talking about the periodic table. It's a lot of fill-in notes and it's a lot of slides, but I'm going to move through them fast. The only reason that it's a lot of fill-in notes is because there's a ton of pictures. Because we're dealing with the periodic table today. A couple things you need to do for this week. The first one is you need to make sure that you take notes, fill those in, and put those in the assignment. There's going to be a form going out asking you about the new grading policies and if you're aware of those policies. And then the last thing is going to be your assignment. Just can you read things from a periodic table and get all that information? So let's get started. Okay. So what is a periodic table? Move me around. Periodic table of elements is a tool that scientists use and have organized so that they can quickly predict the properties of elements. Those properties include metals versus nonmetals, mass, subatomic particle numbers, that's your protons, your neutrons, your electrons, your valence electrons, and your chemical properties like melting point. So at what temperature does solid turn into a liquid? Reactivity, how much does it react? Is it violent? Is it slow? Is it quick? Things like that. That's what we mean by chemical properties. Okay? Just as a heads up, the blue words are the words that you are going to need to fill in. I didn't make them yellow this time. All right, so this guy right up here is Dmitry Mendeleev. And in 1874, Mendeleev published his version of the periodic table arranged by atomic mass. Atomic mass, which is kind of like the mass number, is the number of protons and neutrons in an atom's nucleus. He being Mendeleev, knew that physical and chemical properties of elements were related to their atomic mass in a periodic way. He arranged the elements so that groups of elements with similar properties fell into vertical columns on the table. This direction is vertical, up and down. Oh, move me again. So what we see on this side is kind of what Mendeleev's periodic table looks like. What's interesting about this is that he left holes where in his periodic table, where undiscovered elements were supposed to be. This was beyond kind of the 63 elements at the time. I really want to highlight this one right here. You'll see that this is aluminum. There's the mass. But this guy, there was nothing there. That's an undiscovered element. But this one in particular is correctly predicting the existence of gallium. So gallium is right here. That element was discovered in 1875. So Mendeleev published this periodic table in 1874, predicted that this element would be here. And then in 1875, gallium was discovered, and it's found to have the similar properties that Mendeleev predicted. So he said, hey, there's an element here. It's probably going to have properties A, B, and C, just like boron and aluminum have properties A, B, and C, or something similar. And that's what they discovered in gallium. So pretty cool. So there's a lot of information that we can gather from the periodic table. We're going to first talk about what's in each little element square. And that's this guy right here. I don't know where to move me. I'm going to do that right there. The first thing is our element name, which is this guy right here. It can tell us, oh, hey, this is carbon. Not every periodic table has this, but periodic tables that I want you to use do. Your element symbol, again, this is just the atomic symbol, the thing that tells you, hey, this is the shorthand version of the element name. Your atomic number. Remember, your atomic number tells you how many protons are in an atom of carbon, which is this number right here. If it is a neutral atom, it will also tell you how many electrons if it's neutral. Oh, I don't know if I should edit that out. I probably won't. Okay, so atomic number tells you protons in an atom, and it tells you electrons if it's neutral. If it's not neutral, then those electron numbers are going to change, but those proton numbers won't. So this atomic number guaranteed will always tell you the number of protons. Remember, your atomic number also tells you the identity of the atom. So if I had 6 protons, it's going to be carbon always. If I have 7 protons, it's going to be nitrogen always. If I have 1 proton, it's going to be hydrogen always. The last little bit is this number down here. That's your atomic mass. This is the relative mass of the average carbon atom. We have to say average because this is the same element can have different masses. Those are called isotopes. We're going to talk about them later in a couple weeks. Our mass number will be protons plus neutrons, and that will be a whole number. But the atomic mass is kind of the average. And so we have some carbon atoms have a mass of 12. Some carbon atoms have a mass of 14, so that's 2 more neutrons. Things like that. And we'll talk about what isotopes are later, but know that this is an average. If you're looking at your mass number, this will be a whole number, not this decimal, because we can't have partial or quarters or halves or fractions of protons and neutrons. That doesn't happen naturally. All right. So finding protons, neutrons, and electrons from the periodic table. So this is what you'll see typically. You'll have the name, your atomic number, your symbol, and your mass number. We can see that our element name is right here. It's beryllium. We can see our atomic symbol or element symbol is right here, is Be. The atomic number is going to be 4, and that's this guy right here. And your mass number is 9. So how do we know how many protons, neutrons, and electrons there are? We assume that it is a neutral atom. So the atomic number is 4. That means I have 4 protons. Because it's a neutral atom, we have 4 electrons. Your number of neutrons is equal to your mass number minus your number of protons. So in order to get 5 here, I took 9, subtracted 4, and I got 5. So 9 minus 4 equals 5. My mass number minus my number of protons or minus my atomic number will give me neutrons. Guess what? You get to try it on your own. So pause me a little bit. Pause me and try and do this on your own. But since you're pausing me, I don't have to wait. So I'm just going to go right ahead. I look at this here. I know that I have chlorine. So there's my element name. Oh, I clicked everything. There's my element name. My element symbol is Cl. I have an atomic number of 17. I have a mass number of 35. So I know that my proton number is going to be the same as my atomic number. That should be 17. My electrons, I am dealing with a neutral atom here. I know that it's neutral because I didn't say otherwise. So you don't see any plus or minus charge anywhere around this element box. We assume that it's neutral. So I'm assuming that it's neutral. That means I also have 17 electrons. And then in order to do my neutrons, I'm going to take my mass number. I'm going to subtract my atomic number here. So this minus this, and I should get 18. Oh yeah. So let's double check. Good. So we got 17 protons, 17 electrons, and 18 neutrons. I got this number because I did 35 minus 17. We're going to do the same thing for oxygen. Oh, I won't stand in the middle. Okay. We're going to do the same thing for oxygen over here. I'm mirrored in my thing. Whatever. Over here. And we have oxygen. We have oxygen there. 8 as our atomic number. Our atomic symbol is O, and our mass number is 16. So I should see oxygen, O, 8, 16. There we go. Oxygen, O as an element symbol, 8 and 16. Then when I look at my protons, electrons, and neutrons, my protons is my atomic number, 8. My electrons is equal to my protons because I have a neutral atom, also 8. And then my neutrons is 16 minus 8, which lucky for us is 8. So I should see 8, 8, 8. And I do. Hopefully you got those answers too. If you didn't get those answers and this still doesn't make sense, make sure you send me an email so that I can answer your questions for you. Okay, so there's a lot more information that we can tell from the periodic table. Oh, that's going to bug me. There's a lot more information that we can tell from the periodic table, and that is because of how they are organized. So the groups are the vertical columns, these guys up here, of the periodic table. Elements in the same group have similar chemical properties. So they are very reactive or not very reactive. They explode in water or they don't explode in water. All of them in that column will have those similar properties. And this is because the elements in the same group also have the same number of valence electrons. So we talked about last week that a valence electron is the electron on the outermost shell of your atom, the farthest away from the nucleus it can possibly be. Those are the electrons that do the chemical stuff that we see, the bonding, the reactions, things like that. So if they have the same number of valence electrons, they should have similar properties as well. Now, that's groups, that's vertical columns. Periods are your horizontal rows. And my arrow should be right here, and I don't like that. But periods are horizontal rows. The elements in the same row have the valence electrons in the same energy shell. Because every single row has its own little number that's saying, oh, I'm in energy shell 1, or 2, or 3, or 4, 5, 6, 7. That's as far as we can go. Because the table is organized this way, distinct patterns emerge, including the separation of metals, nonmetals, and metalloids. But Ms. Marshall, what are metals, nonmetals, and metalloids? I'm going to tell you. A metal is all of these purple things right here. Everything under here is considered a metal. Notice how it is to the left of this staircase. And we'll talk about the staircase later. But all metals, except for hydrogen, are to the left of the staircase. Metals are shiny. They're good conductors of heat and electricity. They're very high density, which means if I have a small, teeny tiny amount, it'll have a lot of mass. They're malleable. That means that they can be turned into different shapes. We see that a lot. Even if I looked around my classroom right now, or you looked around your house, you'd be able to see metal in a lot of different shapes and sizes. Also, metals are ductile, which means they can be stretched really thin into thin wires. Cool things about metals. Non-metals, those are the green things here. Non-metals are everything to the right of this staircase, and hydrogen. Hydrogen kind of sticks out over here. Non-metals are dull. And when I say dull, that just means that they're not shiny. Lots of fabrics and paper is non-metals. So this is organic material. Organic material is out of carbons and nitrogen and oxygen. Not very shiny. Whereas metal, right here, shiny. Okay, so non-metals are dull. They're poor conductors of heat and electricity, which means they do not conduct heat at all very well. They're very brittle, so they can break very easily. They could be solids, liquids, or gases at room temperature, whereas metals are typically always solids, except for some fancy ones like mercury. And I lost. Where's the other one? Oh, bismuth. Bismuth and mercury both kind of are liquids at room temperature. They're also not ductile, which means they cannot be stretched. They're very brittle. If I try to stretch it or move it or shape it in any way, it would be very difficult to do that, and it would break. Okay, so those are your nonmetals. Those are your green things. Now, what on earth is this staircase thing? Those are your metalloids. Metalloids have properties of both metals and nonmetals. They're every element on the staircase. So some periodic tables you'll see will have the highlighted elements as your staircase. Some periodic tables that you see will just have a line going through, or it will go right in between. So it's most everything that is touching the staircase. My periodic table in my classroom has just the line. This doesn't have anything, so you kind of need to know where it is. But every periodic table that I'll give you will hopefully have that line. If it doesn't, then I will fix it. I'm going to come back up here. Other things, they are shiny like metals. Some of them are, but they're brittle like nonmetals. So it looks like a metal, but it cannot be stretched or shaped like a metal can be. A couple silicon right here and germanium, these two guys right there, are called semiconductors. So we have really good conductors, we have poor conductors, we have semiconductors. That just means that they can conduct electricity in certain conditions only. You know, certain temperatures, certain pressures, certain, just conditions. I don't know what those conditions are. I wish I could tell you. So we see that each group in the periodic table has its own unique chemical properties, and therefore it has its own unique name. You guys colored your periodic tables right before you left. We all left. And so some of these will sound familiar already to you, but we never talked about properties. So let's dive in. We have our group 1, which is our alkali metals right here. Nice and pretty. They're very reactive. If you put these in water, explosions, huge explosions. I suggest looking it up on YouTube. It'd be pretty cool. They have very low melting points, which means that they're still solids at room temperature, but I only have to heat it up a tiny bit to get it to liquefy. They also have one valence electron. Here's the trick. Everything in column 1 is going to have one valence electron. There's a pattern here. Remember that. Let's talk about group 2. Group 2 is your alkaline earth metals. They're called alkaline. Alkaline is another fancy word for a base. Versus, like in terms of acids and bases. And these guys will react and usually form pretty strong bases. They are less reactive than group 1, so I can put it in water and kind of be okay. Maybe not too large of amounts. They have higher melting points than group 1 does. They are still solids at room temperature, like most metals are. But these group 2 elements have 2 valence electrons. Group 1 had 1. That includes hydrogen, only has 1. Group 2 had 2. Interesting patterns. Let's keep going. Groups 3 through 12. This big block right here, kind of minus these two guys. These guys are down here, but this big block, this is called your transition metals. They're used to make alloys, and alloys are homogeneous mixtures of metals. Now, we remember, hopefully, what a homogeneous mixture is, and that is two compounds or two elements coming together to form a mixture where you cannot see any separation and cannot be separated. So we make a lot of alloys, things like brass and steel. Those are made from your transition metals. They have very high melting points, higher than group 2. And they'll have 1 to 2 valence electrons. That depends on kind of where it is in this block. You don't have to know which one has which valence electrons. We're going to focus on your main group elements when it comes to valence electrons. But transition metals, they could have 1 to 2. It depends. Group 17, we're over here now. These are called your halogens. We're in our non-metals. These are the most reactive non-metals. So these guys will react a lot with these guys to form natural compounds. They bond with groups 1 and 2 to form salts. Not table salt, even though some of them is. Chlorine and sodium will make sodium chloride, which is table salt. But a salt is just a metal, group 1 or group 2 metal combined with a halogen. That's the definition of a salt. And what's also cool is that this is group 17, or sometimes called group 7A. And lo and behold, they have 7 valence electrons. Group 1 had 1 valence electron. Group 2 has 2 valence electrons. And group 7 has 7 valence electrons, or group 17. Cool stuff right there, huh? Last one is group 18, and these are your noble gases. Noble gases are very non-reactive. They don't want anything to do with you. They do not care. They're like, sure, I'm just here, being me, being happy. Their outer electron shell is full with 8 valence electrons. So here in group 18, we have 8 valence electrons. In group 17, we have 7 valence electrons. In group 16, you guessed it, we have 6 valence electrons. 15, we have 5. 14, we have 4. 13, we have 3. Remember, we skipped this one. In group 2, we have 2 valence electrons. In group 1, we have 1 valence electron. But we're focusing on the noble gases right here. And they are happy. They rarely bond with other things. They do bond. Xenon will bond with fluorine sometimes. And there's reasons why that you will learn in chemistry when you take it with me. But all in all, the noble gases here, they don't really react with anybody else. They're happy just being on their own. Okay, let's talk about rows, and the rows or the periods. They are horizontal groups. What period an element is in will tell us what energy level the valence electrons are in and how far from the nucleus they are. That tells us a lot about our properties. So we're going to focus on the Bohr model. Remember, the Bohr model shows us the kind of rings and where electrons are in rings, but we all know that that's not really the case when it comes to the actual model of an electron. It's more like clouds and not rings, but we still like to think of them as shells. So hydrogen, which is this guy right here, is in row 1, which you can't see. Row 1, row 2, row 3, row 4, 5, 6, and 7. Hydrogen is in row 1. All of these guys have one valence electron, but hydrogen's valence electron is in the first shell. There's our nucleus. This is where the valence electron is. It's very close to the nucleus. Francium, which is all the way down here in group 7, or row 7, my bad. That means that one valence electron that it has is very far away from the nucleus. So you can see here's your valence electron right there. It is in the 1, 2, 3, 4, 5, 6, 7th shell. And they have all these electrons in between. But 7 has this one valence electron, which it shares just like hydrogen, is in the 7th shell versus the one valence electron in hydrogen, which would be in this shell. So the row that it's in tells you how far away the valence electron is. This also tells you the relative size of the atom. Every time we add an energy shell, and we're talking about sizes, francium is much bigger because it has more shells than hydrogen does. So periods help. We have 2 unique periods. That's at the very kind of bottom of your periodic table. These guys right here. And these are called your lanthanides and actinides. So your lanthanides, which is this top row, and your actinides, which is this bottom row, they have very unique properties due to the placements of the electrons around the nucleus. Lanthanides, right here, are radioactive. That means that they'll break down and change into different elements. And they behave differently from other metals and transition metals. But that's lanthanides. Lanthanides. Actinides are soft and silvery metals that behave like transition metals. However, the cool thing about actinides is that they are pyrophoric, meaning that they spontaneously catch fire when exposed to air. So when we store elements like this, especially uranium, thorium is a very strong metal. Uranium and plutonium are both very radioactive, just like lanthanides. But when we store them, we have to store them in this special non-reactive oil that minimizes their exposure to air. Because if we expose them to air, then poof, they would just catch fire. Which I'm not going to lie is really cool. I've seen it once. Yeah, so we don't do a lot of chemistry with them, especially in this class. And that was really short, but don't worry. I will never, ever, 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 ever make you memorize the periodic table. It's to be used as a tool. I'm not going to make you memorize every single placement of every centimeter on a meter stick. That's just unnecessary. We use it as a tool to measure things, just like we use the periodic table as a tool to help us understand a lot of different things about different elements. You will learn how to use it in this class, hopefully, even more when we start chemistry. And of course, I had to add all my chemistry puns because now you guys are learning chemistry enough. You understand that I am in my element when it comes to chemistry puns. How often do I tell chemistry jokes? Periodically. My favorite one is this one. I would tell you a chemistry joke, but all the good ones are gone. Yeah, that's pretty bad. I know that it's silence in this room because there's nobody in here, but I guarantee if I said that in front of your class, then it'd still be silent. And this one too, right there. Do you see it? Oh my God, I can't believe it. It's the element of surprise. I say all these things because I just miss you so much, and I want to be able to give you a laugh in a time that's very difficult for everybody, whether or not you stay at home and you have a good home life or a not so great home life. Hang in there, wash your hands, don't go outside, don't get into groups of people, minimize exposure, take deep breaths, practice mindfulness. I love you all. I cannot wait to see your faces next year. Remember, if you do not have me next year or you didn't take chemistry, make sure you pop by and still say hi because I'm missing a lot of you, a lot of your faces. All right, hopefully I didn't move too fast, but that's everything that we know about the periodic table that you need to know. Make sure that you do your assignment and upload a copy of the notes that you took in this video.